All right. Hey, everybody. I thought it'd be, instead of just music at the beginning of the show, we'd do something actually, useful. So, I love lockpicking. It's a hobby that I took up a couple of years ago, and I'm still practicing. I'm still getting better. But I find that there are a lot of software hackers that also do a lot of lockpicking, just because some of the same mentality goes along with it, right? It's using a tool against its intended design, right? So let's do some lockpicking before the show starts. I don't know if you've ever done any lockpicking or looked at how a lock works, but when you start in lockpicking, you get these practice padlocks, and they look kind of like this. So what you're looking at here is a transparent, acrylic body for a lock. And then you have the core of the lock, right? That has these different holes for the pins that go into the core of the lock or the cylinder. So basically the way that it works, right, is that when you have a keyed lock like this, you have two pins, right? You have a driver pin, you have a key pin, and they're spring loaded, right? That's why they come back down. But the idea is that this right here, the separation between them, when that separation meets up with the very top of the cylinder, when all of the pins, which are of different lengths, meet up with them, then the cylinder can rotate. And that's why your key has differently leveled areas on it called bitting. That allows the pins to slot into the right position, and then you can turn the key. So what lockpicking is trying to do is exploit the fact that there's a little bit of play in the cylinder, and that the holes that are drilled into the cylinder are not perfect. And so what we're trying to do when we're doing lockpicking, at least this kind of lockpicking, is we're trying to basically catch, using tension on the cylinder. We push the pins up and then kind of move it off of position so that the driver pin falls and separates from the stack. And as we do that for each of the positions, we reduce we unlock the lock. So let's see if I can pull this one off. This practice lock is actually a little bit tricky to do. So lockpicking explained. So you need two tools, right? You need a tension tool to apply tension to the lock, and I'm going to be using this guy right here. This is called a top of keyway tension tool. And what is going to happen is that it slots into the top of the keyway, like so. I'm left-handed also, so everything is backwards for me and harder. If I were right-handed, this would actually be a little bit easier, but that's how I got made. So, and then the other tool you need is a pick. So I'm using this nice Southord pick, which I ordered from Lockpicking World. And so we hold some tension in there, and we go through, and we gently try to press the pins into position. And the transparent lock is nice is because you can kind of see what you're doing as you go, right? You can but you want to learn how to do it by feel. And the idea is that each pin is going to have, if it's ready to go, it's going to give some resistance to your pick. That's your key. That's your indicator that that's the one that you should push up to try to pick next. And let's see here. I think I have pretty much everything set except for pin number 2. 3 is overset. And I lost my key. Yeah, this tool is actually kind of a pain for this key, or this keyway, just because it's so wide. That feels pretty good. Oh. Ah. Okay, well I did have it. It just, the tension tool came out. Let's try a different lock. This is an actual lock. This is a master padlock. It's funny too, because they have these like really, really strong shackles, right? By the way, if you want a good lockpicking YouTube channel, go check out Lockpicking Lawyer. That guy's the man. But so they have a really like a boron carbide reinforced shackle, right? So you can't like use bolt cutters or fence cutters to get through it. But then the body of the lock is really weak, and also the lock itself is really weak. That practice lock that I was playing with has 7 pins in it. Or it has 6 pins in it, rather. The 7th is a null position. So it has 6 pins in it, right? For a practice lock. This has 4. So I only have to deal with 4 pins in this lock. Let's see here. And sometimes you reset it just to make sure you're hitting everything. Come on. It's funny, I was like practicing on this lock before I started the stream, and it was opening every time, and now of course doesn't want to play ball. Oh. And we're open. If I can actually get the quarter turn. There we go. Nice and simple. All right. So I'm going to try one more. This is a bit of a harder one. Well, it's actually not that hard. Let's try this other master lock. Again, super reinforced shackle, pretty strong body, and it's got this recessed keyway that's spring loaded to try to prevent you from being able to pick it too easily. And I'm going to use a different tension tool for this one. I'm going to use this Z-bar. That's nice and strong, and this one actually slots into the bottom of the keyway, and I'm using my thumb to maintain tension. If I were right-handed, how would I do this? If I were right-handed, and this is how you'll see most people do it, right? I'm using my ring finger and my pinky to pull, right? And then pick with my right hand. But if I try to do that, I'll never get it open. So let's see here. There are other picking methods as well. There are other tools. Some of them kind of look like little saws or something. And those are for raking. So basically you aggressively go at the pins kind of all together to randomly set them in position. And that works and it's fast. And if I were doing like a lockpicking race competition, that's what I would do first, just to see if I can, just to save time. But this is called single pin picking, right? Going 1 pin at a time. And it takes, you know, more skill in a way, because you have to feel what each pin is doing and then adjust accordingly. Almost on this one. If I don't get it this time, no big loss. I'll shoot for it next time. This is actually good because it's an incentive for me to keep practicing. Oh, there we go. Yep. Just need a little love. Master locks are not, some of them are really simple to pick. Some of them are built simply, but then just because they're like so shoddy, I find they can be difficult to pick. Like this guy, right? Everybody has this padlock. It's the, like, I think it's the most common padlock in America. Well, it's in theory one of the most simple to pick just because there's nothing special in it. It's four pins. It's not hard. But because, I don't know, because of its shoddy construction, it's very hit or miss for me whether I can open this lock. I can rake it every time, but single pin picking, a little bit trickier. Give it a shot. And you go pin by pin and you feel to see if there's resistance on the pin. And if there is, you press it up until you hear a click, and you're maintaining tension on the tension tool so that once the pin goes up into position, the cylinder rotates, right? And then another pin will become tight, and that's what you push on. Oh man. Thank you, Tiny Master Lock, for opening on the stream. Really appreciate that. That was cool of you. All right. So what do we open? We opened 3 locks. It's not so bad. Or what do we, let's see, we did the big circle one. We did, yeah. And then we'll save this guy. This is another master lock I have. This one's actually super fun because it has special pins in it. It has what are called spool pins. So if you can see the pins in here, it's kind of hard to focus on, but they're basically just tiny cylinders, right? But a spool pin has a wide part, a narrow part, and a wide part, right? So think like a capital I or a spool of thread. And the idea is that it's going to try to trick you when you pick it, right? Because the wide part will go up and then catch because you're applying tension. So you'll enter what's called a false set. And you will think that you've picked it into position, but you haven't, because you still have the rest of the pin body that you need to go through. And in fact, if you keep pushing up, you'll catch on that bottom wide part. So you have to like ease off the tension, rotate the cylinder back, then push it up. So I don't know, there's a little bit more skill involved to that one. I like picking spool pins. And they give you more feedback, right? There's more interesting stuff going on in the hand when you do it. All right. By my clock, it is 10 o'clock. Welcome, hackers, to episode 3 of Hack Summer. I am Michael Taggart, or just Taggart. You can find me at Twitter there. And what we're doing on this stream is we're talking about Python. We're talking about cybersecurity. We are not assuming any prior experience. So if you're just joining us to learn how to code for the first time, you're in the right place. Welcome. On our last episode, we were talking about sequences. And sequences, if you remember, are things that we can loop over. Orders of information like strings, or we introduced lists and tuples where you can loop over them. You can also get specific parts out of them using indexing. We're going to see some of that today again. And you can also append to lists, right, to add to your list after you make it when you start your program. Now, we've been talking in each of these episodes about the 4 fundamental structures of programming. And it's really important to understand these 4 structures because they govern everything, right? They are the absolute basic building blocks of every computer program, at least in this kind of programming language. And that kind of programming language is called a declarative or imperative programming language, where we're writing instructions in order, right? Just as we've done in our previous sessions. So these 4 fundamental structures are going to be there in every program that we write, and we've covered 3 of them so far. So we've covered variables, right, where we store our information. We have covered conditionals, where we execute code depending on whether something is true or false. And then we have loops, where we repeat sections of code for a given number of times or until a condition is met. Okay, so that's 3 out of 4. Today, and this one's a little bit more special to me, but today we're going to cover the fourth, and there's an argument to be made that it's even more important than just one of the four core structures of programming, and that's functions. If I seem really excited, I am. I'm a dork about functions. I don't really know why. And I think it's because once you understand functions in a really deep way, it changes the way you think about programming. What we're doing so far is we're writing instructions in order, and that's a great way to think about writing programs. Once you deeply understand functions, though, there's another way to think about your programs, and we'll get to that toward the end. Okay, so what are functions? Broadly speaking, functions are like tiny programs within your programs that we can reuse again and again. And the basic structure of your function is that we send information called arguments into the function. Then the function does whatever it does. Okay. Right now we're not concerned exactly with what it does. We're just concerned with what goes in and what comes out. So arguments or parameters go into the function, and then the function returns or outputs whatever value is the result of the function. Now, some of you, if you remember your middle school and high school math, may have done functions in math, and we'll talk about how functions in math and functions in Python relate. But I want to be very clear that you don't have to be a mathematical wizard to understand functions at all. Quick aside, I do programming as a professional now, but I failed algebra. Okay, and I was an English major in school, so there's no kind of necessary mathematical prerequisite. I think some people often will have the feeling that they need to have majored in math or majored in computer science or something like that, or have that kind of mind. You don't. You can get at this from a bunch of different ways, from a bunch of different angles, and we're going to do that. We're not just going to do mathematical functions today. In terms of why we use functions, as we said, they're tiny programs within your program so you can reuse code. But it's even more interesting than that. There are three specific problems in programming that functions solve. The first is modularization. What we want to do when we write a program cleanly and efficiently, and to use kind of a word that's overused in the profession, elegantly, we want to break things apart so they're readable. We want to break our novels into chapters, right? We want to break our essays into paragraphs, things like that. Well, functions kind of provide that same sort of separation. That if we think about our program as a set of discrete tasks, if we can kind of chunk them up in reasonable pieces, we want to define them inside of functions. A couple of reasons for that, in addition to just separating them out visually or logically. When we break them out that way into functions, then when we are testing our code, especially a lot of code, we can test each individual function to see if that function is doing what we expect. So that's called a unit test, where we test each individual function, and then we'll do what's called an integration test, where we test the whole program to see if the whole program works as expected. The second of the three big problems that functions solve are something called deconstruction. This is a really important habit of mind for new programmers, where what we want to do is when we have a really nasty problem, like a really big, complex problem, that's not really how the computer's going to think about it, and it's not the way that we should be thinking about it either. So what we want to do is we want to take that big, gnarly problem and break it down into its component pieces, and then write the solutions for those smaller, easier to solve problems. Again, modularization and deconstruction kind of work together. So with functions, we're really, really trying to get at, solving the smallest possible problem and then kind of scaling up from there. And then finally, abstraction. So what we'll often find when we're writing our code is that we will start by writing a solution to a very specific problem. But then we will find other problems that are kind of similar that we need to solve. And with functions, what we can do is we can write a single solution that handles all of those similar problems. It's like, I guess almost like building a screwdriver with multiple bits, or just you want to have a function that I'm falling apart on my metaphor here, but the idea is that the function is flexible enough that the specifics of the instance of the problem don't matter so much, because we're going to give the function those specifics when it runs, but that it's built to handle all kinds of different situations that are related to that kind of problem. And that'll make more sense when we jump into it. So let's jump into it. Let's write some functions, see how they work, and then we will build some cool tools using functions. All right, I'm over here in Replit. If you've joined us before, you should be familiar. If not, go ahead and go to repl.it and sign up for an account and start a new REPL and choose Python. So you should have a screen that looks like this. Drinking on mic, very professional. It's just coffee though. All right, so the first thing we're going to do is we're going to write a function, and we're going to revisit some concepts that we've seen before. So we're going to write a function called greet, and it's just going to say hello like we did in our first episode. We create a function by using the keyword def, short for define. So def greet says that we're defining the greet function. Now, greet functions when we define them have parentheses after their name. And inside of those parentheses would be the names of the arguments or the parameters that we are sending into the function. This will make more sense when we start actually building the function. But for now, let's go ahead and put the word name in there. Now, we've used the word variable before to talk about things like this, to talk about placeholders for information. I want to not use the term variable in this case because it's not quite that. It is information that's going into a function that's a little bit different than a place where we're storing information. So this is called an argument or a parameter. I'll put that in on the comments. It's either called an argument or a parameter. Okay, so inside of the function, it's Python, so we're going to indent. What we're going to do is we're going to print, and we're going to do it just the way that we've done before, right? Hello, plus, and then name, right? And then plus the exclamation point. Okay. That's it. That's all we're going to need for now. Go ahead and click run. And if you do have any questions, feel free to drop them in the chat. I am watching it as we go, so feel free to ask questions there. I will answer them as best I can live. Okay, so we have hit run, but of course nothing has happened. Why has nothing happened? Because there is a difference between defining a function and using a function. Really, really important distinction here. Defining a function tells the interpreter, tells Python what to do when the function is invoked, but does not actually invoke or call the function. To call the function, we use the function name, and then we give it specific information inside the parentheses that relates to the arguments or parameters that are defined. So if I want to greet myself, I'm going to say greet and then the string Taggart, and then that works. And then I can say, right, great heck summer. So the function was loaded into memory, which is why we have it available over here, and it works, but we have to actually call the function. This is referred to as calling the function. If we wanted to have it just run that way inside the program, when we hit run, we would do the same thing. We would say greet like that, and that itself is actually calling the function. So why is that so handy? Well, let's imagine that we had a bunch of names, right? And so I've got a list just like we've done before. You know what? I'm tired of my name. Let's go DS9. Go Cisco, Kira, Odo, Dax, Esri or Jadzia, Worf. Am I missing anybody? Important. Quark, of course. And Morn. Okay. For name in names, greet name. That was super confusing. I apologize. So let's call it N for N in names. Greet N. So what's going to happen is that we're looping through this list of names. N is going to refer to each of these strings in turn. That string is going to be passed to the greet function, and then we're going to get the greeting for each of these characters in turn. Cool. Now, this is working so far. We have our basic function. However, this is really, really important. This is not the way that we should. This is not the way. If you've been watching The Mandalorian, this is not the way that we write functions generally. What we want to do with functions is, as we talked about in the intro, we want to return or output values that we can use in our code. Printing is cool, but we don't save that information anywhere, right? It goes out, but we don't save it. And that's unfortunate because I actually want to do something useful with, I may want to do something useful with the information. So we have to learn about another keyword that we use inside of functions called return. Let's change up the print to a return statement. So we do return and then get rid of that parentheses at the end. Okay. Actually, I shouldn't have deleted that loop, but let's go ahead for N in names. Let's remake it. Print. Oh, no. We'll do greet N. Okay. Let's run it, see what happens. Nothing. Because we're returning the value, we're gaining access to that information inside the program, but we're not telling it to print anywhere. If we wanted to print it, we would have to wrap this greet here inside of the print function. We would have to wrap that like so. Because what we're saying is print the result of the greet function with whatever n is. So we're returning the value. Why does that matter? Well, if we wanted to save the result of the function for later, let's say we had another list, right? I don't know why we would do this, but let's say greetings equals an empty list. And then we would say G equals greet N. So now we have a specific string, which is the greeting, right? And then we would say greetings.append, there's our list again, G. So now we're saving the greetings themselves inside of this second list. Let's run this. Okay, now if we ask for greetings, you can see that we have all of the greetings saved. The return is important for testing as well, because if we want to test each function in turn, we have to test its output. If the function doesn't have any output, we can't test it. So you want to write your functions. You can write them to have no output like we did originally with that print, or just do stuff, right? We call them side effects that you can't see, but there's a really poor programming practice. So we're going to try to write our functions as though we need to have a return from each of them. Okay, with that in mind, let's go ahead and make a new REPL. and we're going to call it, we're going to revisit some old code here. We're going to call it Caesar Funk. All right, that's what I'm going to call it. It's not going to bop as much as Uptown Funk. There's nothing I can do about that, but it should be fun. So what we're going to do is we're going to functionalize or functionify our Caesar cipher. So if you remember our Caesar cipher, we are taking the alphabet and we are shifting the message using that alphabet by a given number of spaces. So we're going to make our constant alphabet, and by convention, we all caps our constants. And now we're going to write our Caesar function. And our arguments are going to be the message, which I just shortened to MSG, and the shift amount, however much we're going to shift the message. Okay. Here's another fun trick for writing functions. It's a great idea to kind of call your shot, to kind of Babe Ruth it, by which I mean, think about where you want to end up. What do you want to return out of the function? Well, at the end of the day, what do we want from this? We want the encrypted message out. So we know that we're going to have to start with an empty string where we're going to put our encrypted stuff, right? Why is this yelling at me? Oh, right, because I haven't used it yet. And then return encrypted. So it's like, we say, okay, we know that we're going to start with encrypted, and then we're going to do stuff, whatever that is. And then at the very end of our function, we're going to return it. This is a really, really effective way of writing our functions because it keeps us on track, right? We know we have to go from here to here, and whatever we do to this has to mean that what we get out of the function is what we expect. So I tend to refer to this as calling your shot in functions, where it's like, you know, name the pocket in pool or something like that. I don't spend a lot of time in bars. I'm not that cool. That's why I learned how to do this instead. But what do we remember that we need to do? We have to go through each character in the message. So for C in MSG, what are we going to do? We're going to have to use the alphabet and shift it out. This is where the modularization really, really comes in handy, and that deconstruction. Because think about what we're doing, right? We are shifting each letter of our message, right? We're shifting each letter of the message, or substituting each letter. If that's true, why don't we, instead of writing all of that nonsense here, why don't we solve the small problem first? So the small problem is, how do we take a single letter and move it to the right position in the shifted alphabet, right? So let's write another function up here called substitute. And we're going to give it two parameters, two arguments, letter and the shift amount again. So we're going to shaft the shift amount here. So this function is going to take a single letter and shift it. If we solve that problem, then all we have to do is loop over and do that a bunch of times, right? This is why deconstruction is so important, because it makes our thinking much, much clearer about what we have to do. And it often reveals that very, very tricky problems are simple once we break them down. So how do we shift a single letter? Well, we have to first check that the letter is in the alphabet like we did before. So we'll say if letter, remember in does a check for us against a sequence to say if this is part of this sequence, then we are going to do some stuff. We'll say shift the letter. We'll just leave that for the moment. Again, because we're going to call our shot here. And then we're going to return something if that's true. But if it's not true, else, we're just returning the letter, right? We're going to pass it right through. No funny business. Here's something fun. Return is a showstopper when it comes to functions. Meaning that once I'm inside the code of a function and I hit a return statement, that exits out of the function. No other code So if I had like return letter print, couldn't find it, if I had this statement inside, it's inside the function, right? It's indented. This will never happen because the return ends the execution of the function. This line will never execute, cannot happen. Because that's true, and we're going to put a return statement inside the if too, we actually don't need this else. You'll see what I mean in a second. We'll leave it for the moment. So we're going to shift the letter. How do we shift the letter? Well, remember that we have to kind of find the index of the letter in our alphabet and then add the shift. So we'll say idx equals alphabet. Remember that find, and we'll look for the letter, and then we will add the shift. Now, last time we did this really, really convoluted, like separating or subtracting the difference between that number and the length of the alphabet and all that to try to loop back to the beginning. Now, the reason we did it that way is because we had not yet explored the modulo operator. And if you remember, the modulo operator gives us the remainder from integer division. So if I do like 25 mod 5, right, it's 0 because there's no remainder to that division. 25 mod 4 gives me 1 because there's a remainder of 1. So this is cool because it actually does the looping for us in this case. So let's say I had like the resulting index of my value was like 30, right? So 30 on 27 is 3, right? Which means the remainder is what I actually need to goes back around to the beginning, right? Because 30, you think 0, 1, 2, 3, that would be D. So that loops around appropriately. The other really handy part about this is that there's no upper limit, right? I could give it a really dumb number. Like I could say our shift is like 500. I don't know why you would do it that way, but you could. It should be 26, sorry. And look, the remainder is reasonable because it's just the remainder. You can divide as many times. We don't care about that. We only care about how many is left over. So all this to say that our looping instruction is going to be much cleaner this time because we have the modulo operator at our disposal. So what are we going to do? We're going to return. So we're going to return a single letter out of the alphabet, which means indexing, right? We have these square brackets that we're going to use to go get a specific index from alphabet. What is that? It's going to be idx modulo the length of the alphabet. And again, I like to do it this way. You could hard code it to 26 if you want. I like to do it this way just in case somebody wants to change their alphabet. So we've written our substitute code, and there's our return statement, right? So if the letter is in the alphabet, we'll do this and then return this. Because there's a return here, and there's nothing else that we want to do, we actually can omit this else, and just unindent this return. So if this test is true, we'll get into this section of the code and then we'll hit this return. If it's not true, we just boop, go right here. And we don't have to worry about the else. You can write the else, it's totally fine. But I just wanted to make it clear that because of the way return statements work, you can actually omit it and your code works fine. Let's actually test it right now. I'm going to write a pass, which is just kind of a placeholder to say I haven't written this code yet. So I can run my code without errors right now. So let's actually try it. Let's say substitute C with a shift of 5. D, F, G, H. Okay, cool. Let's give it like a shift of like 300. Okay, so we're not getting any errors. It looks reasonable to me. So we have our substitute working, which means it's pretty simple to get our full Caesar encryption working. So we're going to do we have the message, and then we're going to say encrypted. We're adding to the string. Remember, string concatenation, so we can do plus equals the result of the substitute function. Substitute with C, the letter, from the message, and then the shift amount. And then we return encrypted, as we said before, right? So we got to where we needed to go. Let's run this. Let's call Caesar for hack summer. And again, notice that I'm using the space and the exclamation point, so the substitute should pass those right through without messing with them. Oh, good. So I forgot to give it the shift amount, right, as my second argument, and I got the error that says so, right? It says we're missing one required positional argument shift, which is saying, hey, you forgot to give me the second thing here, comma, let's say shift of 8. Pixacums, that's what we had last time. Let's give it, 800. Okay, that's different, but it does work. So with the mod, the substitution works a little bit better, but also now we have the ability to reuse this function again and again. Now, if we wanted to run the code straight, we could, of course, call the function, right? We'd say print and then Caesar of whatever we wanted, and then that would output it right inside the code. But we can also just load it into memory and use the interpreter this way. Quick preview of next week's session. We're going to kind of turn this into a little bit more of a real scenario, by which I mean we're going to start using the command line, like the terminal on a real computer, to interact with our Python programs outside of the Python interpreter, which is really handy because then we can give the program that we're running information at runtime, like the message that we wanted to encrypt. Right. Any questions on our Caesar? No? All right, then let's quickly take a break from the code as we talk about what we're going to be doing next. Okay. I have taught this next thing, I don't know how many times. I feel strongly that every programmer needs to do FizzBuzz. If you aren't 10 and you don't remember this game, so FizzBuzz goes like this. You start counting. 1, 2. When you hit a number that's divisible by 3, you say fizz instead of the number. So 1, 2, fizz. 4, when you get to a number divisible by 5, you say buzz. So 1, 2, fizz, 4, buzz. Fizz, because 6 is divisible by 3. When you get to a number that's divisible by 3 and 5, you say FizzBuzz. That's the game. And it's great for teaching factors. You can do FizzBuzz with different divisibilities, different factors, but 3 and 5 are kind of the canonical original flavor of the game. And why it's so important here is that FizzBuzz is an entry requirement when you are doing a coding interview. So if you decide you want to become a programmer, and you say, I'm fluent in Python, the odds are pretty good that somebody's going to sit you down and say, write FizzBuzz in Python. There are some reasons for that. One reason is that FizzBuzz, if you do it correctly, contains all 4 fundamental structures of programming that we've talked about. So it demonstrates that you have an understanding of the basis of the language. And people solve it different ways, so it also gives the interviewer an insight into how you code. Everybody has a slightly different coding style. So let's do some FizzBuzz, and hopefully this will serve you well in the future, and also give us some more practice with functions. All right, new REPL. FizzBuzz. I was really expecting it to be like, you've written this, you've used the FizzBuzz file name 20 other times, so you can't do it again. Okay, so again, we want to think about the big problem and the little problems, right? So the big problem is that we need to go through for a given amount of steps, right? We can say we're going to loop up to 1,000 or whatever, and we're going to run FizzBuzz up till then. We're going to write that in our main function, and this is a very important programming pattern. We have a main function that kind of is our default for running the program. And what we're going to say is we're going to do FizzBuzz for a given number of steps. And we'll define steps here. Steps equals, and say, like, we'll do 30 for now. It doesn't really matter yet, but, and then we're going to do for I in range 30, because we're going to loop. And then what do we have to do? We're going to kind of call our shot here as well, where we're going to say FB equals, and then we're going to say it's going to be the result of our FizzBuzz function. Don't worry about the angry green and red squiggles. We're going to get rid of them as we go. And then we're going to print FB. Okay, now I'm kind of breaking my own rule here with main, because what are we not doing in the main function so far? We are not returning anything. So main is often one of those functions that doesn't return anything. You can if you want, and actually there are like exit codes that we'd use on operating systems to tell the operating system kind of how the program ran, whether it ran successfully or it errored out. So you could like return 0 or something like that. But for now, it's okay that the main function doesn't return anything. To call the function, to make the program actually run, though, down here we're going to have to say main, right? That actually kicks it off. In some programming languages like C and C++, when you compile the program, it'll look for the main function, and then that'll be kind of where the program kicks off automagically. And you don't have to manually call the main function. Python doesn't do that. So if you want to use the main construct, you have to manually call it like this. Okay. So we know that we have kind of the big loop solved, right? We're going to just do FizzBuzz a bunch of times. So what is FizzBuzz? Well, let's write that function, def FizzBuzz. You'll also notice that I am writing the support functions above the main function. You don't have to do that, but I like doing it because, again, it's an ordering of the information. So if you're a programmer that's coming to this code base and you don't know anything about it, you gotta understand what you're looking at. So it's easier to understand the component pieces first, and then if you need to skip down to the main, you can say, okay, this is how all the pieces are put together. But I like putting the supporting functions up top. So FizzBuzz is going to take a single argument. We're going to call it n, which is the number that we're trying to test. Interestingly, this is where thinking about data types really comes into play. Why? Because FizzBuzz takes an integer, right? And if it's divisible by 3, it's going to return fizz. That's not an integer, that's a string. If it's divisible by 5, it's going to return buzz. And if it's divisible by 3 and 5, it's going to say FizzBuzz. Those are strings, so the actual signature of the function is that it takes an integer and returns a string. We have to be very mindful of this idea, what a function takes in and what it sends back out in terms of data types. If we forget that, we will get confused when we start using the returned data. It's a very good idea. In Python, you can have a program return different data types, or a function return different data types, depending on a condition or whatever. You could have you could say if n equals 0, return false, else return 1. My point, we're not going to do this, but this is a Boolean data type, right? And this is an integer. So the same function, depending on what n is, will return an entirely different data type. This is a very bad idea. Do not do this if you can avoid it. And we can avoid it here. Okay. So what are we going to do? We're going to test for divisibility. When we're doing conditional tests like this, where there are multiple options, we always want to test for the least likely first. And that's because conditionals fail down. And you'll see what we mean in just a second. So we're going to test for divisibility by 3 and 5. So we have a couple of ways that we could write this. Obviously, we can say if n mod 3 equals 0. Remember, we're using that divisibility. We also have a Boolean operator in Python, so we can say and we'll talk more about that later. N mod 5 equals 0. That's FizzBuzz. Before we go any further, is there another way we can write this? It's funny too, because I used to write it this way every time until one of my students was like, you can just say, You can use the first number that is divisible by both 3 and 5. So you can actually use just 15, which is the same test. Okay, that's as mathy as we're going to get, I promise. Well, sort of. So we have this. So we're testing for FizzBuzz now. Now we have to test for fizz or buzz. It doesn't really matter which one we do next because they're both equally as likely. So we're going to do elif. There's our elif because we have more than 2 conditions, right? Elif n mod 3 equals 0, return fizz. Elif n mod 5 equals 0, return buzz. And then lastly, if it's not divisible by anything special, it's just a number we don't care about, you might think just return the number. But wait. String, number. Crap. Before we return this thing, we have to convert it to a string. You don't have to, but I think you should do it. So that way we guarantee, just like that, that'll convert your integer to a string. By the way, I should have mentioned this a while ago, but if you ever want to know what data type something is, you can wrap it in a type function and test it. So if I do type hello, it tells me that it's a string. If I do 4, it tells me it's integer. 4.0 tells me it's a float. False. And then lastly, okay. So use type to find out what something is in case you're not sure. All right, so we have FizzBuzz written, looks pretty good. And oh, I didn't actually use the steps variable. There we go. All right, let's give it a shot. So why did we get FizzBuzz first? because we started at 0. So all of those tests are going to pass. So we can tell range to start at 1. And if we actually wanted to go up to 30, we would do steps plus 1. There you go. 1, 2, fizz, 4, buzz, fizz. 15 gives us FizzBuzz. There's our FizzBuzz. So, check it out. Variables, conditionals, loops, functions. It's the quick brown fox jumps over the lazy sleeping dog of programming. It has all the pieces very quickly, very efficiently. If you can write FizzBuzz, you know the language pretty well. All right, any questions on that? Yep, so somebody in the chat is saying that it's a good thing these videos are recorded because it can, they're a little backed up. It can take some time. You know what? That's okay. And I should actually point out that is intentional, meaning that do not expect to just watch these videos once and get it. That's not how we work. That's not how brains work. Repetition is necessary for understanding. And so it's okay to have to watch these a couple of times and go through them slowly. I'm going through this admittedly pretty quickly just so we have the information, but it's okay to rewatch them. It's okay to take your time with this. There is no, at least from my perspective, there's no time constraint here for you. You learn at your pace, right? This is something that hopefully you're doing for yourself because you want to, and that is okay. All right. So the next piece of the next function we're going to write, I said that this was as mathy as we were going to get. I kind of lied. I forgot that we were going to do this next thing, but it's really fun. So hopefully it'll be worth it. Fibonacci. The Fibonacci sequence. Fibonacci sequence, if you're not familiar with it, very simple concept. So you start with the numbers 0 and 1. Okay? You start with 0, you start with 1. You take those two numbers and you add them to each other to get the next item in the sequence. Now you've got the current number is 1. You add them together, what do you get? Okay, you add that and the previous together, what do you get? 5, you see where we're going, right? 8, 13. There's a whole bunch of science about how the Fibonacci sequence shows up all the time in nature. It's sort of related to the golden ratio. There's a lot of kind of, I think, pseudoscience about it, but Fibonacci numbers have a weird way of showing up in lots of different places. Fibonacci spirals are pretty cool. Lots of plants tend to have Fibonacci numbers of leaves or branches. I don't know why, but the Fibonacci sequence is a fun, again, thing to learn how to do. So we're going to create a program that generates the Fibonacci sequence, and it does it for, however many steps, very much like what we did with FizzBuzz. So we're going to start with main. Same thing, we'll do steps equals, say 20. And then we're going to call Fibonacci for steps. Or we can do it this way, right? For I in range steps. Need that colon. print Fibonacci I. Okay. So we have our main function, but we have to write Fibonacci. Let's go ahead and do that. Def Fibonacci, it's going to take a single number and whatever that number is. I'm thinking through this here, and I don't think I want to do it quite this way. I actually want to abstract this a little bit more, just for my own clarity. So I'm actually going to I'm going to write it this way. I'm going to do that n is actually the steps and give Fibonacci the steps. So I'm going to put the loop up in Fibonacci, meaning that all I'm going to do in main is like literally this. Okay. So what are we going to do? We're going to, with Fibonacci, we're going to kick off, we need two variables. We need to hold the current number right in the previous number. If you remember the sequence, right, we were going like 0, 1. We added those together to get 1. We added those together to get 2, right? So whenever we are trying to create the next step in the Fibonacci sequence, we need the last 2. So we need two variables, at least. But we know we need 2. And we know that we're going to start at 0. And we know that we know kind of the next one in the sequence. We know that is going to be, we could say a plus 1 if you wanted, or you can hard code it to 1 to start it. Either way is fine. Now, we have the steps coming in, right? And actually, let's make that clearer. Same thing. So for I in range steps, we have to change A and B. This is where it gets a little bit interesting, because it's like, okay, what can I say? So if I say A equals B, like A equals what? So if I try to change B first, I say, okay, well, the new number, whatever it is, right? The new A is supposed to be kind of the sum of the last 2, right? So I say A equals A plus B, but then what's B? So like I have this parallelism problem where I start changing values that I need for both of these. And by the way, we're going to print B for each of these. That's the number that we want to print out. So we're going to start it at 1. So because the first sum, if you think about it, is 1. 0 plus 1 is 1. So that's the first number that we print out. But then we have to change them, right? So we have to say, okay, the new A is equal to B, right? We switch it up, and then we say B equals A plus B. But oh no, we already changed A to B. This is very confusing. So what we need is a way to kind of assign these values at the same time. We could have a placeholder, or we could say like old A, right? But there's a cooler way to do it that we actually already know, which is to use a tuple. So I'm going to actually write a third function up here called fib. You can call it whatever you want, but I'm going to call it fib. If this were Haskell, I'd call it fib prime or Fibonacci prime, but we're not in Haskell, so fib. And fib just takes two values, A and B. And here's how we're going to kind of cheat this. You can assign values at the same time if they are in a tuple. Remember, tuples are like lists. They're inside parentheses, and they can't be changed. But because you can return tuples as the result of a function, we can actually get two numbers out of this at the same time. So we do return b a plus b. So this is how we're translating these values into the new values at the same time. And in terms of assignment, what do? Because we're returning the tuple this way, we can actually assign the values the same way. So we do at the same time, a comma b equals, actually works, fib of a and b. So we're sending off these a's and b's, whatever they are, off to the fib function. The fib function does our transformation, right? Changes a to b. And then gives it back to us. And so again, we're going to print b. What didn't I do right? Let's see. Try and range steps. AB equals fib AB. 20. Oh, forgot to call main. Good job, Taggart. There we go. Now the program will run. Fibonacci. All right. Any questions on the Fibonacci sequence and how we kind of broke this down? There's a bit going on here. The first is that we learned how to return multiple values at the same time from a function using tuples and parallel assignment using tuples. It's a fun trick. And it saves you some code if you need to have those placeholder variables, right? With like old A and old B. You could have done it that way, but I find this a lot cleaner. And again, we're breaking our problem down into smaller and smaller pieces and using functions to solve those small pieces of the problem and putting it all together. You can see how this is a much different way of doing things than what we were just doing before. Okay. Since we do have some folks in the room who are talking, I do want to ask if we go over the hour to get to the last thing we want to do, is that preferable, or do we want to call it at the hour? I can go either way. All right, well, I think I feel compelled to give you the cybersecurity angle. So there's just a little bit more that we need to do. So let's talk about generators. There are very often situations in programming where you're going to be dealing with very big values and a lot of values all at once, or in a loop. And it may not be the best idea to save all of those values at once, right? Or to generate the list all at once. That's what generators are for. So generators are this fun kind of a function that will produce a different value every time we we increment the function, and you'll see what that means. Generators are really poorly understood in Python. People don't use them that often, but they're really, really handy in very specific circumstances. And I want you to at least see them so you understand kind of how they work, especially since they have changed a lot since other versions of Python. So I want to show you how they work now. And what we're going to do is we're going to use the Fibonacci sequence that we just did, and we're going to combine it. We're going to combine it with some encryption ideas. So what we want to do is we're going to make an obscuring function where we kind of pad out a message, and all we need to decrypt it is the number of, like, the starting point for the Fibonacci sequence. What does that mean? So, like, if we have the message hello, what we're going to do is we're going to take H and then pad out a Fibonacci step number of random letters in it, and then E, and then the next Fibonacci number letter, Fibonacci number of random letters. So you'll see that, like, it obscures the message pretty well, and this is what's called, it's the introduction to what's called steganography. Should have made a slide for that. I will write it in the comments when we do the code. Steganography is the art of hiding messages in other messages, or hiding information inside of information. So it has nothing to do with the Stegosaurus. I'm very, very sorry about that. The Stegosaurus is rad, but that's not what we're talking about. Okay, so with that out of the way, let's jump right in and make our Fibonacci-based encryptor using generators. All right, go ahead and create a new REPL. We'll call it FibEncrypt. Okay. The first thing that we're going to do is we are going to write the Fibonacci generator function. So we're going to make a new file actually for this and call it fibgen.py. So this is going to be a supporting file that we don't run, but it's going to contain code that we need to use in the main file. This is a really important pattern to get used to, and it's related to the abstraction that we talked about in the deconstruction that functions are so useful for. All right, so again, we're gonna take our previous Fibonacci code and kind of modify it. So we're gonna say def fibgen and say n. It takes the number that we're gonna start the sequence at. By the way, you can add default values. So if somebody forgets to add a value for an argument or a parameter, you can actually specify what the default is inside the function definition, and you do that with an equal sign. So say default started at 0. Then we'll say A equals n, B equals n plus 1. So again, we're starting the sequence here. And this is where generators really get kind of confusing, because generators like this are going to rely on an infinite loop. An infinite loop is a loop that doesn't stop on purpose. What does that look like? Well, we're going to write while true. True is always true, so the loop will never stop. If we like did while true and then print something, this will run forever and eventually break your computers or crash the program, either one. So don't do that. Be very aware of infinite loops. Be very wary of them. But in this case, we're going to do something a little bit different than that. So we're going to do the same thing that we did before with A, B equals fib, A and B. And let's just go ahead and rewrite fib up here, or you can copy and paste it from your old file. Def fib, A, B, return B, A plus B. Okay. Here's the part that's going to be very different. Instead of the return keyword, we use the yield keyword. Okay. Why does that matter? Let's run this. Nothing's going to happen. I'm going to import FibGen. So from FibGen, import asterisk. So I'm importing all of the functions from here. Now, a generator has to be stored somewhere because it produces this thing called a generator object. So I'm gonna call it gen equals FibGen, and we kick it off at 1, let's say. If I look at gen, it tells me that it's a generator object, right? Totally weird. We haven't seen this before. And I can't call it. Like if I say gen of 1, like it doesn't really work. So what do I do with this thing? So generators are built to work with this built-in function in Python called next. So if I ask for next of the generator, see, it gives me that. And then next time I call it, it gives me that and that and that and that and that. So that's actually how we're going to do this. So we have the generator done. This takes people a long time to wrap their heads around, like what's going on with this generator. So I just wanted to introduce this to you. I highly recommend going and reading the documentation at docs.python.org about this. But yeah, generators, useful when you have to generate a lot of values in sequence, but they would be prohibitively large to store all at once. That's when you would want to use generators. Okay, we have our FibGen. Let's go ahead and write the encryption code. So head over to main.py. We're going to need two things here. We're going to import random because we're going to need the random library or the random module. And then we're going to do from FibGen, same thing we did in the interpreter, import asterisk. Now, let's make our alphabet again. All right, and then let's go ahead a few lines down and write our main. And we're going to say MSG equals hello, right? And then we're going to do print obscure hello, or that was dumb, print obscure MSG. So we're going to have to write this obscure function, whatever that is. We haven't written it yet, but we will. And what that's going to do is it's going to take each character of the message and pad it out with a Fibonacci number of random characters. Def obscure takes the message as its argument. And same thing we did really with the Caesar cipher, right? Encrypted equals empty string, and then we're going to go ahead and return encrypted. There's our calling our shot again. So we have to get from here to here. Okay. The first thing we need is we're going to need that generator for our Fibonacci numbers. So let's go ahead and do that. Let's do gen equals FibGen. Yeah. And then n equals 0 is fine, right? Or we can give it, you know, wherever we want to start it. I'll start it at 1 actually, so that at least we start it with some padding. Okay. Then we have to go through each character in the message. So for C in message. We have to add the letter, the part that we're not obscuring to it, right? Encrypted plus equals C. And then we're going to also add the padding. And we have to write it. I'm going to write a new function for this called pad. And what are we padding it with? Well, we're padding it with a Fibonacci number of random characters from alphabet. So I could say this in another variable. So I could say like fibnum equals next from the generator. Or I can just take that next from the generator and pass it right over to my pad function. Either way. I like doing it this way because it saves me some lines of code, but it is also less clear. So it really depends on how you want to write your code. I will write it this way for clarity now, so that we're sending the Fibonacci number over to the pad function, which we haven't written yet. But we're going to. And the argument here is the pad length. Okay. Padding equals empty string. And then we call our shot again. We say return padding. So whatever that is. And then we'll use a different kind of loop actually for this one, right? So we could say like for I in range pad length, but we don't need I, right? So we have another way to do this. We'll use a while loop for this. We'll do while the length or len of the padding is less than or equal to the pad length, whatever that number happens to be. So we'll keep doing this as long as our padding is smaller than the maximum size. While that's true, we're going to add something to padding. Padding plus equals, here's where random comes in, random.choice from alphabet. And then we return the padding. So this function right here takes a number, happens to be a Fibonacci number, right? And then we create a random amount of padding for each of those numbers. And then as we go through our message, right, we're creating a new Fibonacci number. We're adding the real character to it, but we're also adding a Fibonacci number of random letters to it. That's kind of it, guys. That's it. So if we hit run here, every time I forgot to call main. There we go. Let's try that again. So you can see that it's like there's a lot going on here, but it's definitely working. So there is our encrypted message. Now, something that you can do if you want is try to write the decryption algorithm for this. So let's say you knew this was the encryption method. Could you try to decrypt it using different starting points for Fibonacci numbers? That might be a fun exercise for you. All right, that about covers it for today, but I wanted to end about this idea of thinking functionally. It is a little bit different than the way that we've been writing programs up till now, which is instructions in order. Sometimes we'll have conditional, sometimes we'll have loops where the things repeat, but it's pretty much just steps in a recipe. That's a totally valid way of thinking about your programs, but there is another way of thinking about them. And functions really lend themselves to this way of thinking, which is changing the shape of data. Imagine, you know, those like those toys for infants where they have like the different shaped holes for the different shaped objects, right? And passing them through. Imagine a series of those, right? Or a series of like cookie cutters or something where you're reshaping an object piece by piece by piece, like an assembly line. Functional programming is something like that, where you take data from a starting point, you pass it through a series of functions, it gets transformed through those functions, and ends up in a completely different shape at the end. That is a different way of thinking about your program than just instructions in order, but I think it's a really valuable way of thinking about your program, because it forces you, one, to think about the steps from beginning to end, where you want to end up, and also it forces you to think about the kind of data that you're working with, right? As we saw in FizzBuzz, the data type that you're working with really matters. So thinking functionally is a great way of getting into that habit of thinking about data types as well. All right, that about does it for this week. But before we get out of here, again, if you're enjoying what you're seeing and you're finding some value in it, I encourage you to donate if you can, not to me, but to an organization that is trying, just like this program is, to bridge the digital divide. Human IT is doing so by making low-cost internet connections and computing devices available to families who need it. You can go to human-i-t.org to donate financially, or if you have old computers that are in good shape, they will take them. So go there, check it out, give if you can, please. Thank you so much for joining us. Next week, we are going to break out of the Python interpreter. Actually, literally, we're going to kind of hack Replit to do this. And we're going to get a command line on a computer and learn how to interact with the terminal or the command line on the computer and understand how that works with Python, so we can write real programs with real input. Thank you so much for joining us. We'll see you next time.